me out with the start of this course. Because I have to assume that you all had everything through Calc 2, and I know what that means, but coming from different backgrounds, you're going to have to tell me what makes sense and what doesn't, and I want you to please raise your hand and just ask me to re-explain something today, if you can. Because that'll kind of give me a little guidance, okay? My plan in the first half of class here is to at least get through some of the intro to this idea, some calculus ideas. And then in the second half of class, you'll notice it says calculus of these vector-valued functions, whatever that is. I hope to just give you lots of examples in the second half of class. So maybe the first half of class has a little more theory, and the second half of the class has a little more practical examples like what you're going to see on homework. That's what I'm picturing. And we'll take a break kind of in between. So the 10-minute break, it won't always be the same place, all right? But if you guys tell me, hey, let's take a break, you know, that's one signal that I'll use. Sometimes I need a break, okay? But it's built in, and we'll get to it. All right, so it's funny because we're talking about what are called, well, let's do this. Lines and curves in space. Okay? But I want to give this a mathematical setting, and I want to explain everything that I'm doing. And so I'm going to start off with what we mean by space, right? Again, that's the theme of Math 2700, is that space is how many dimensions? This is three-dimensional space, right? And so what I'd like to do is I'd like to introduce this notation. You guys familiar with that? Yeah, what's it mean, though? The real numbers, as opposed to fake numbers. Imaginary numbers, right? I was just explaining this to linear algebra yesterday. I threw that R on the board. They didn't know what it was, although we've seen it. But again, it's against the complex numbers, okay? So in this class, you guys are kind of lucky because we are going to keep it real. But what we're doing is we're going to write this as R3. And that set, again, if the real numbers are every number that's on the number line, I'm going to have three number lines, namely the x-axis, the y-axis, and the z-axis. And the way I'm usually going to draw them is something like this. I like to make my y-axis go out to the right. They have it a little bit slanted. My x-axis comes out here. And so again, the traditional calculus world that you worked on back in Calc 1 or Calc 2 is all contained in this little plane, right? And then you have here, this is the z-axis. So to me, this is my way of representing R3 on a piece of paper. Does that make sense? And what is R3? It's a set of what? Ordered triples? Nice, Kathy. Some people would say it's a set of points. But these points are equivalently, ordered triples. Every point can be represented by three numbers, x, y, z. Right? And so, for example, I could plot, 1, 2, 3. Let's do that as an exercise. Try and get my artistic skills going here. Let's see. So along the x-axis, I want to move 1. And along the y-axis, now what I try to do is I try to make my tick marks parallel to the x-axis. I find that helps the illusion a little bit. So my x is 1 and my y is 2. And then if I kind of draw this parallelogram here, this point right here has the coordinates 1, 2, 0. Right? And then I can fool myself by moving up the z-axis. Let's see. We want to move up 3, so I'll call that 1, that 2, and that 3. And then what I can do is I can kind of reproduce that parallelogram so that I have these nice vertical lines. Does that look three-dimensional to you guys? Yeah, you don't have to lie. Well, I'm trying. If you keep everything parallel, I was always taught that works. And then, you know, 1, 2, 3 could be this point up here. Okay. So that's fine. Well, what about lines? A line in three-dimensional space, you know? How do I graph that? Well, there's a trick, and I'm going to kind of work through what your book does, okay? I've seen this before. We use what are called the parametric equations of a line in R3. X equals X initial plus AT is one of them. Y equals Y initial plus BT is another one. Oh, I should slow down because I used a math word. I have to try and make sure we define each of these today. Parametric. You guys studied parametric equations? How do you know already that I'm probably talking about parametric equations when I wrote these two equations down? There's kind of a giveaway. What is the parameter up there? The parameter. Which one? T. T is the parameter. We like to use T as my input when we have parametric equations. Sometimes we use it anyways, because T stands for time quite often, right? There's one more, which would be, you could probably write it down without me doing it, right? Z initial plus CT. And how is it that this works? How can these equations automatically give me a line?
They're plotted along all three. Like time will be what it's plotted along.
Okay. So if you think of T as time, that really helps us in terms of visualizing. Yeah. You can think of, I mean, really X here you can think of as a function of T, right? Same with Y, same with Z. And in each one of these cases, these are linear functions, right? If you were to graph each one of these separately versus time, your slope would be here and your intercept would be there, and you could plot that. You could plot each one of them against time and you'd see lines. But what's going on here? What I'm doing is, I'm in the world of space. Here's X, here's Y, here's Z. I don't see time. Although with my ebook I can. Now we'll do that, we'll go there next. Right? But what happens is, okay, I have a point here somewhere in space. I'll call it P0. What are its coordinates? Or P0 if I use the German 0. X0, Y0, Z0. Right? So that's the point, which is somehow a point on the line. Actually, it's a very important point on the line. It's the point on the line when T equals what?
No,
0, right? And then if T is positive, then we move somewhere. And so let's suppose that when T is 1, we move to here. Well, this is what I might call a vector V. Okay? Now, in our calculus book, we denote vectors. Well, first of all, I'm going to put a little arrow above my variable to tell you guys I'm talking about vector, although I might forget it sometimes. Our calculus book is going to use boldface. Boldface, and we'll try to use letters like V to tell you, hey, this is a vector, right? So V equals a vector A, B, C. And a vector, what is a vector? Didn't Despicable Me explain that? I have magnitude and direction, right? So now everyone knows. I love that. So, but it doesn't depend on position. You can move a vector, right? All I know is that if I start at P naught, I'm going in this direction, okay? And so if I go in that direction, times whatever T is, right? You could scale this by T, then you're going to move some distance along this line. So if T equals 2, I guess I'd be at this point. If T equals 3, I'd be at this point. You could see copies of vector V, right? What if T is -1? Can you do that?
Yeah.
Sure, you could say it came from here, right? So you can see that this set of parametric equations is going to move you along this line corresponding to that vector, which is where vectors become extremely important, okay? And as a matter of fact, we can rewrite the equation, because if we want to write it using vector notation, this is really kind of cool. We can say x, y, z is equal to x naught, y naught, z naught plus ABC times t. What did I just do? I tried to make a shorthand for writing those three equations. Now what you might not see is, how did you suddenly have 3 vectors? And this is a very important point. Here, I want to go back to the picture I drew here of 1, 2, 3. And I'm going to draw this vector right here, starting at the origin. What are the coordinates of that vector? Well, if you start at the origin, it's easy. 1, 2, 3. I move 1 in the x direction, right? That's how I plotted the point 1, 2, 3. So there's this one-to-one correspondence between the points, the ordered triples, and the vectors in R3. Now, it's interesting. We're going to use this bracket notation for vectors. We're going to use parentheses when I'm thinking about these objects as just singular points. But at some point, we want to kind of blur that and be able to go back and forth. Think of a vector, think of a point. You're really thinking of the same set. There's just as many vectors as there are points and vice versa. That's pretty easy to see because all you're doing is changing the symbol outside. You guys with me? Now, back to my equation, okay? We had up here the parametric equations of a line in R3. What I'm going to give you here, okay, would be the vector equation of a line in R3. So here I go. This is a vector, right? X, Y, Z. It corresponds to some point. I mean, where is it? I don't know. Here, pick a point in space somewhere. Boom. That vector right there, that's X, Y, Z because it points at point X, Y, Z. You with me? So what I'm going to do is I'm going to give it a vector name. I'm going to call it R vector equals. This one I'm going to call R naught. R equals R naught plus, now I already gave this one a name. I called this one V. V is what you might call the direction vector. Of the line. Times t. What is t? We think of it as time for our visualization, yeah. But as an object, is t a vector? No, t is that's the word I'm looking for. It's called a scalar. A scalar has magnitude only. So it's a real number, because again, we're keeping it real. In other more abstract classes, you might allow complex numbers for t also, but we're not going to do that. So this is the equation of a line. Oh, one more thing I might do, which may actually shed some light on it. Are you guys okay if instead of R, if I put a little parentheses and put a T here? What kind of notation is that called? Function notation. You familiar with what I'm saying? It means that what's in parentheses you can think of as input, right? So if I input 0, where am I? R naught. If I input something else, I'm somewhere else on the line. So this is a linear function. And I took time doing this. This is usually done at the end of Calc 2 as well. But I thought maybe this would be a nice transition. Because what we're going to do today is we're going to talk about other functions, R of t, that are not necessarily linear, but they do have vectors as outputs. And when I write this symbol, I want you to think, oh, the output is some point in 3 space, or some vector in 3 space. Again, they're interchangeable. So if you look at what the book does, this is really kind of nice, I think. We'll zoom down a little bit here. Yeah, they talk about vector-valued functions. They talk about lines in space. Let me go there now. And they're going to do a similar presentation to what I did here. But here they have, this is kind of cool. Hey, where do you want x naught and y naught? You can play with this at home if you want. I can move things in the x direction, the y direction, the z direction, and I'm changing the line. But you'll notice this is not changing what about the line? The direction. If I want to change the direction, I have to change the direction vector, A, B, C. That's kind of nice. And again, you can change t. There's a negative value, there's a positive value. When it's at 0, we're right at p naught. Okay. So, fine, that's nice, but you can't really do much calculus on lines. Although, hey, let's do the quick check. We haven't done that yet. So I'm going to give you a wit whack, right? What if this were a quiz? Okay, so we're going to do quick check 1. And why don't you say good morning to someone next to you and work with somebody for a few minutes. I'm going to pause the recording. I don't need to record this. And then we'll go from there. All right? Try problem 1 with. So we want to talk about curves now. Curves in space, right? And so in general, curves in space you can also define using R of t vector notation, maybe a little bit easier than you could do other ways, right? So instead of writing it like I did before, how about I write it this way? F of t, g of t, and h of t. Each one of these is a function right out of college algebra, let's say. Okay? And together, you put the outputs of those three functions together, and that tells you what point you're at for r of t. So in the example we had before, right, if I go back up and zoom out just a tad before I turn the page here, remember we were talking about these lines, right? This is my f of t, that next one is my g of t, and the next one was my h of t. Those are all linear functions in the very first example we did. But you don't have to use linear functions. You could make one of them a quadratic, or a rational function, or a trig function. And so we want to do those kinds of things, and then we're ready for calculus. Okay? And as we do those things, we find we have curves. Okay? So let me throw a few examples at you, and we'll see what you think. So here we go with some examples. Suppose I write r of t is the cosine of t, I, plus the sine of t, j, plus 3 times the vector k. All right? And now I'm tapping into some ideas from maybe Calc 2 or maybe your trig class as soon as I start throwing cosine and sine up there. So I guess the question that I want you to talk to your neighbor about is, what might this curve look like in space? And again, I'll pause for a moment. Go ahead. Talk to each other about that. I'm going to write that this entire curve is in the plane z equals 3. Because, right? There's no t here. I don't care what point I'm talking about. So if I were to think of this, you know, I guess what happens is that I have to go up 1, 2, 3 units, and I'm only in this plane right here in 3 space, right? And now what shape do we have? Yes, what kind of circle? A unit circle, right? Remember learning that x is cosine and y is sine? You may have learned x is r cosine theta and y is r sine theta, right? I mean, what is a circle? A circle is a set of points that are all the same distance from a particular point called the center, right? So, yeah, if I were to sketch this graph, I guess the graph looks something like that, right? Okay, this is the path that we're tracing out with our another way to see it is to think about distance. The distance from 0, 0, 3 is always 1, right? Because, well, you could use the distance formula. Do you guys know the distance formula? Sure you do. What's the distance formula? There we go. Plus. Yep. Is this true, by the way? Can I do this? Plus z1 minus z2 squared. Does it still work?
Yeah.
Yeah, we usually prove that in Calc 2. I don't know if you guys did. I love proving it in Calc 2, but I'm not going to do it today. If you want to see sometime, stop by. That's a fun proof. So that's the distance formula, right? And so again, if I realize that I'm trying to measure the distance from this point 0, 0, 3, that can be point number 2. And so what I have here, I don't care what t is, I have the cosine of t minus 0 squared plus the sine of t minus 0 squared plus, and now the z coordinate is always 3, but then that's minus 3 squared. So 3 minus 3 is 0, so I can kind of forget about that piece. Oh, and then what? you get the square root of cosine squared plus sine squared equals 1 for any value of t. That was the identity I learned in trig class. The square root of 1 then is 1. So I thought that, I wanted to throw that example of you because it reviews some ideas that are going to come into play. But the fact that cosine and sine give you circles and the fact that you have this identity, it's kind of nice. So let's try another one. Suppose I have r of t equals cosine of t I. Better be a little bit neater, Paul. Let's zoom in too. Try again. Cosine of t I plus cosine of t j plus radical 2 sine of t k. Well, I guess one thing that's interesting here is to think about the fact that, you know, there are 3 parametric equations again. What are they? X is equal to what? It's what's next to the I, that's right. So my parametric equations are x is equal to cosine t, right? What about y? That's also cosine of t. And what about z? Yeah, it's radical 2 sine of t, right? It doesn't mean I know what this looks like. Maybe, I don't know how long it would take for you to sit and think of maybe doing this. But let's do it. I'm giving a hint. I want to do x squared plus y squared plus z squared. No, I can compute that. I get cosine squared t plus cosine squared t plus what? 2 sine squared t. Did that help us? Apparently not. Did it help you?
I've seen this equation before.
Yeah? My computer's having trouble here. So, what I'm thinking here, well, I just used it. Cosine squared plus sine squared is 1, right? So if you take the fact that you have 2 sine squareds here, put one of them there and one of them there, yeah, you get 1 plus 1, right? I love a calc class where I can write 1 plus 1 equals 2. So my equation says x squared plus y squared plus z squared equals 2. What is that? Yeah.
It's a sphere that has a radius of radical 2.
Good. Because, right? X squared plus y squared equals 2 is a circle with r square root of 2. And it's true that if you generalize, and again, why? Well, it all goes back to me doing this distance formula in 3 dimensions. But if you believe this equation, which you guys said, okay, then you believe this equation probably is a sphere of radius square root of 2. And then, well, now what? Well, okay, there's another fact I know. Also, x is equal to y, correct? Well, if x is equal to y, what shape is that in our space R3? Maybe it's more apparent if I write it this way. Y equals x. What's that look like, guys? Now that's a line if you're in R2. But see, in the world of R3, let me draw it. Here's x, here's y. We just kind of dealt with that line. In the xy plane, right, it's a line. But if we're talking about 3 space, it's actually a plane. Do you see that? Because I didn't tell you what z is going to be. Is that, oh, that's making it worse. Well, you know why? What I did wrong was I drew my line, but I didn't keep these lines parallel. There's a little bit of art that you should have when you're going to teach Calc 3. Then, how do you draw a sphere? I find you draw the equator and then you kind of do this kind of stuff. But more importantly, even if your students can't view your picture, they can understand if you tell them, hey, I have a sphere and I'm cutting it with a plane. By the way, my lunch day I do it this huge orange. I can show you guys, right? So when I cut it in half, what shape is the curve?
Cool.
It's a circle. That's right. It's what you might call a great circle on this sphere. In that plane, right, it would be kind of zooming around this way. Isn't that cool? I noticed your book had an important picture that I wanted to share with you. When they did curves in space, and they said, by the way, guys, we haven't done any calculus yet, so now it's time. In order to do calculus, we're going to talk about limits, and we're going to talk about continuity. And why do we need to talk about those things? Because what do you think I want to do next? If I want to do calculus, I want to take the derivative. That's right. You know, we have right here some function r of t. And what I would like to do is I would like to next think about r prime of t. Because what kind of things do you get from derivatives? You get what? Headache, yeah. Well, you get a calculus class. No, why do we do it? Why do we take derivatives? What do we get from that? Rates of change. What else? Slopes of tangent lines, right? Remember all this stuff? Well, it's all coming back in 3D, okay? So we want to do that. In order to do that, we need to talk about limits. We need to talk about continuity. Yes, question?
No, I'm just trying to visualize. Are we like doing a plane on the sphere is tangent to the sphere?
It's a good question, what you just asked, and I want to show you a picture. And is it here? No, it's in the next section. Which is where I really, oh no, it's got to be there. I missed it. Bring it back. Come on, picture. Oh, I see it. Not lines in space. It's under curves in space. I thought it was under the calculus. Orientation of curves. This is important. Okay? So, here are 2 pictures of curves. Which one looks like the one that I just graphed? B. Partly because it's a circle, but also because it is what's called parametrized. You see, when you plot this circle, I was very sloppy here, and that's okay. But you have to understand that I could compute some points by plugging in values of t. Give me a value of t that we could plug in and get a point. No.
0.
0 I could do. The cosine of 0 is 1. So I'd be at 1, 1, and what's the sine of 0? So I'd be at 1, 1, 0. That's one of the points on this circle. 1, 1, 0. Actually, it's right there. It's on the line y equals x, and it's, okay? And I also have 0, 0, 1 if I plug in something, well, 0, 0, square root of 2, I guess, huh? If I plug in pi over 2, okay? So it's interesting because the point that the book is making here is that when you have a parameterization, you actually have a direction you're moving around the curve. It's called an orientation. And we are going to take derivatives and we're going to talk about tangent vectors. And a tangent vector only moves in a certain direction, which is good. Remember we had our vector v was pointed in a certain direction? And if you want to go the other way on the line, you had to put in a negative value. Same thing is going to be true here. The tangent vector matches the orientation of the curve. You were asking me, what about the surface, the sphere? Can we have a tangent plane? And the answer is yes, we will do those kinds of things in the next chapter. Okay? So I did want to answer your question, but I felt like this is really important to understand. We're about to take the derivative, and when we do, yes, there are tangent vectors. That's the picture that I want you to have. Okay? So let's do some calculus. So what first? Well, I guess we should define a limit. And then I have to watch my time, because limits take a long time. All right? I mean, I'll show you. I'll show you. Yeah, let's do it. The book defines limits, and I had to check how serious they got today. Oh, by the way, the rest of this section is all just examples. These are ones that I wouldn't want to do by hand, but you can look at the pictures on your own time. I mean, they're cool. Slinky, let's just show you the picture. It's worth looking at. There's your Slinky curve, huh? Anyways. Yeah, back. It's just too good not to see it at least once. All right, well, that's playing. Limits and continuity. So they say a vector-valued function r approaches the limit L as t approaches a. So they want to define, and let me do it with them. Here we go. Definition. Limit as t approaches a of r of t equals L means, now if you had me for Calc 1, this was a very common quiz or test question, except we didn't have the letter R, we had an F. And we didn't have a t, we had an x. And it was the limit as, you know, it was still x approaches a. But what was the definition that you guys had? Well, I'll tell you what, it wasn't this. Provided that the limit as t approaches a of absolute value of r of t minus L equals 0. That's all they say in your book. And I was kind of like, really? And then I noticed they're doing a little bit here of work, and then they say, where was it? They say we're gonna do a little exercise for you, which I'd like to do now. So, oh yeah, well here's what they say. They say, look, if you want to compute the limit, you compute the limit as t approaches a of f of t. You do it for g of t, and you do it for h of t. You know what that is? That's 3 Calc 1 problems there. You get all 3 limits together, and you put them in a vector, and that's your limit. Okay? It's basically saying, to do limits in Calc 3, all you have to do is be able to do limits in Calc 1. That's what it's saying. Now, can we remember what limits in Calc 1 look like? I'll tell you what. Let me give you my definition of limit, the formal definition of limit. Uh-oh. What did I just write? Upside down A is going to stand for For every or for all? Do you guys know that Greek letter? Epsilon greater than 0. What's the next part of this going to be? There exists, and my shorthand is going to be backwards E for that, okay, which a lot of mathematicians use. Some of you are cringing, but this is good to write down. There exists what? Delta greater than 0. If I have a little epsilon, there exists a little delta, such that if 0 is less than some absolute value less than delta, then, and now, I'll go ahead and write what they have. R of t minus L. We're trying to get R of t minus L to be less than epsilon. And by the way, what is it that goes in here? T minus A. Can I see a show of hands of people that remember somewhere in their past doing an epsilon delta definition of a limit? Only half. Okay. Well, I'll skip this proof for now. I'll skip it for now. It's interesting because the book says that's exercise 78, and it involves epsilon and deltas. But if you just understand what I said, if you can do limits in Calc 1, you can do them here, then you can get away with most of what we want for the book. Okay? Here's another definition. R of t is, I got to show you the page or you can't see it. Here's the word we want, continuous. At a point, so let's say at t0, some time, if, So I want to do this, but I have to think, what's my Calc 1 analogy? Back in Calc 1, we had this definition. F of x is continuous at x equals a if... Okay, so here's the deal. I decided not to do the epsilon delta today, but what I want you to do now is talk to someone next to you about the pink, and maybe then we can complete the definition there. That's the trade-off. So let's pause for 30 seconds while you talk about the pink. Do you remember what it means? So why do I even care what the definition of continuous is? Because a function has to be continuous if I want it to be, the word is differentiable, which means what? Able to differentiate? Able to take the derivative, right? So we want to take derivatives. You have to be continuous first. And what continuous means, it means in Calc 1, limit as what happens? X approaches a of what? Well, of f of x. What is it that I want it to equal? You want it to equal f of a, which is why when you do limit problems, the first thing you ever do is you plug in a. And usually that just tells you what the limit is. And if you get something undefined, you're out of luck, unless you get what's called, do you guys remember what are called indeterminate forms? 0 over 0, then maybe something good can happen. We learned L'Hopital's rule. We learned all kinds of cool stuff. Wow. I mentioned it's going to go faster second half of class. Here we go. So this is the limit as what? Well, we can draw the analogy. We're continuous at t naught. So it's as t approaches t naught, let's say, okay, of r of t equals what? R of t naught. And that makes sense. To be continuous, you need all three component functions, f of t, g of t, and h of t, to be continuous. Okay? So once we do that, then what we understand is that, and kind of this is the take-home message, we have component-wise differentiation. If you get one thing out of today's class, the fact that limits are defined as they are and the fact that we have continuity means I can just take derivatives in a nice, easy way, component-wise. In other words, do f of t, do g of t, and do h of t separately. Okay? So, well, should we do examples? Yeah, maybe it's time. I guess I'll do one more thing. I'll say that we have component-wise integration also. All this good stuff we learned in Calc 1, because an integral is also based on the idea of limits. Okay, it's the limit of a Riemann sum. And let's just say that it all works nicely. So now it's time for examples, and I thought I would just kind of go through the homework from section 2 and work a bunch out. And then send you on your merry way. So let me get this 13.6 up and running. Notice they're going to talk about derivatives, tangent vectors, and integrals. And you guys will do the quick checks. So I'm going to let those go and just jump right to some of the basic skills exercises. And we'll start taking some derivatives. Notice how they write the functions. This is probably a little easier notation than your IJK would be. So I think I'm going to start with problem 14, just for kicks. Well, so we have r of t is given by, and the x-coordinate, it says t plus 1 to the negative 1 power. What's another way to write that, by the way? 1 over t plus 1. And the y-coordinate says tangent negative 1 of t. That does not mean 1 over. That does not mean cotangent. What does it mean? Arctangent or inverse tangent. And then the last function would be what? Yeah, natural log. And so I'm just reminding you of Calc 1 facts when we do this problem, right? If we want to compute r prime of t, all we're doing is we're going component by component. Now, how do I do the first one? Well, I do it using the chain rule in a sense, or the extended power rule. I call it bing, bing, bong. Bing, I write down the negative 1. Bing, I put t plus 1 to what power? Sure, you lower the exponent. And then bong. I take the derivative of what's inside. That's the chain rule. But that's 1. So there's the first component. I'll simplify that in a moment. Second, do we remember the derivative of the arctangent? Very good. 1 over 1 plus t squared. Sullivan, that's nice. Sure is. Actually, you're more likely to remember this next one. The derivative of the natural log, 1 over t plus 1. Oh, but again, the chain rule, right? Ding, dong, right? So we did ding, dong. We need to take the derivative of t plus 1. But again, that's just times 1, right? So again, I should really say what I'm doing here in my notes, I suppose. That's helpful. What I'm doing here is the chain rule. I'm doing the fact that the derivative, which I'll write as d dt nowadays, not d dx, right? The d dt of t plus 1 is 1. Okay, so how do we finally finish this problem? We probably say something like r prime of t is the vector given by negative 1 over t plus 1 squared, comma, 1 over 1 plus t squared. Please tell me that you know that those denominators are not the same. We were reciting in my algebra class yesterday, when I square a binomial, I get a trinomial. Okay, so that's kind of cool. More examples. Tangent vectors. Find a tangent vector at the given value of t for the following parameterized curves. Which one do you want to see? 20?
Let's do one with trig.
Trig. 18. And that has the chain rule too. Let's do 18. Oh, 23 has trig also. Sure. Well, let's do 18. R of t is equal to 2 sine of t, comma, 3 cosine of t, comma, the sine of t over 2. And then they tell me we're talking about a certain, think of it as a time, right? We want t to equal pi, and so I wrote that down. Do I know what this curve looks like? I don't, guys. I don't. I knew the one with the square root of 2, but this is, yeah. But although, actually, you might be able to do something similar. Use an identity. Well, let's not do that. All right, so what we're doing here is just a little calculus. R prime of t would be, what would it be? 2 cosine t, good. This is the one that becomes negative. Negative 3 sine of t. The derivative of cosine is negative sine. And then the last one would be, how about 1/2 cosine of t over 2? Where'd the 1/2 come from? Dong, the chain rule, right? And again, what I'm going to do now is I'm going to say, okay, let's take t equals pi, and we'll substitute in. And when you do, what happens is you get r prime of pi. So, what does that mean? Bless you. It's 2 times the cosine of pi. It's negative 3 times the sine of pi. And it's 1/2 times the cosine of pi over 2. See, we can evaluate it. And when you evaluate this function, r prime of t at pi, you get a vector, which is good. That's the picture I showed you. There's going to be a vector pointing in some direction. So what will it be? What's the cosine of pi? So yeah, we get negative 2 because the cosine of pi is negative 1. The sine of pi is, and the cosine of pi over 2 is also 0. And so which direction is my tangent vector pointing? Yeah, the negative x direction, wherever that is. You could say left, you could say, right? But it's pointed along an axis if you want. It's parallel to an axis. Okay? So that's kind of nice. Now, it says unit tangent vectors is the next section. I don't want to do one of those, but I do want to make this a unit tangent vector. So what I need to do is I need to, I guess, divide by its length. You know, if I call this vector, let me give it a name, v. Suppose v is this vector. Do you guys know how long that vector is? Well, this one's easy. How long is it? 2. How do you get it? The length of v is the square root of negative 2 squared plus 0 squared plus 0 squared. Or you just say, duh, it's 2. Right? Square root of 4 is 2. But it's not a unit vector. How do we get a unit vector? Sure. So the unit vector, u, would be v divided by the length of v. And if you take this vector and divide by 2, I guess you would get negative 1, 0, 0. Which I guess I could call negative I, right, if I wanted. But we're going to find that quite often it's a lot easier to work with unit vectors because sometimes we don't care about the magnitude, we care about, hey, which way is the object moving? And that's what a unit vector tells you. Think of it as a velocity. We did that in Calc 1. Now it's easier. because now the components come naturally. All right, let's see where we go next. I promised rapid fire. Here we go. Unit tangent vectors at a point is pretty self-explanatory. Derivative rules. I skipped those. Thought, well, let's just do an example. So what's going on in problem 32, for instance? You have a scalar times a vector, right? And you might say, well, how do I handle that? Well, there's all kinds of rules that I skipped. Maybe I can show you a few of my notes. Remember I mentioned teaching this back in the Stone Age of Case? Here's their notes, right? Differentiation formulas. Dun, 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 dun. Isn't that just so helpful? No, it's not. So what's helpful, I think, is to maybe do an example here. But what you'll find is there are a variety of product rules, and that's what's going on here. And they're all basically the same. So I guess I could almost give you the choice of which one you want to see. You like 32? Or do you like 36? That's cool. Maybe we'll do both, huh? Well, what about 35? Oh, wow. So let's just talk about what the difference is. 4t to the 8th minus 6t cubed times v of t. That's cool. So that's problem 32. They say, for any of these, what they're asking you to do is they're asking me to find the derivative. Okay.
And I didn't see the directions. Did they give you a V of T?
They did give me a v of t. Maybe I should write that down, huh? So let's do that. They gave me a u of t and a v of t. There they are. So u, I don't want to write it the way they did. I want to use our shorthand. U of t is, I want to use the bracket notation. 2t cubed, comma, see what I'm doing, guys? I'm writing it with this bracket notation. 2t cubed, comma, t squared minus 1, comma, negative 8. And v of t is e to the t 2e to the negative t and negative e to the 2t. All right? So, what's going on here? When they say find the derivative, I want you to understand this guy here is just a function of t, but this guy here is a vector valued function of t. Right? And what I'm supposed to do here is find d dt of this. Now, what's the rule? The great thing that this section is trying to get across to you is if you guess what the rule is, you're probably right. This is a product. Remember products? How did you find derivative of products? We had a product rule. So what did it look like? Well, it's like this. F prime of t times v of t, and then what am I going to write next? Plus is right. Plus what? F of t times v prime of t. Yeah, does that really work? And the answer is yes. And we can prove all this. I'm not going to. The Honors Classic case, yeah, that was lots of stuff what we did. Here, I'm going to sense when to and when not to. And with 2 minutes remaining is not the time to do it. How about 35? Well, that's where they said dot product. I just have a question for you guys. If I do u of t dot d of t, or v of t, is this a vector or a scalar? Good, this is a scalar. Well, when I say that, it's a scalar valued function of t. It's a function that'll return a scalar every time. Whereas, what did you guys learn about cross products? What's a cross product? It gives you a vector. How do you do it? Did you guys learn about taking the determinant of a matrix, IJK? Really? Cool. So you could actually do that here if we had more time. You could throw the I, the J, and the K up here and take the determinant and you'd figure out what it is. Or you could use a formula. I don't care. Did I assign this one? I hope not. Anyways, what's really cool is that the answer, the derivative of this, is what you would hope it is. What is it? It's U prime cross V plus what? U cross V prime. Now let's see if that even makes sense. U prime cross V is a vector. U cross V prime is a vector. If you add those two vectors together, like we did on the board over there, they'll point exactly in the direction that gives you the derivative of this original vector. These are beautiful facts that can be proven. Some are done in the book. Sullivan?
So up there before,
Yes.
on number 32,
Yes.
it seems like it would be easier to do the product rule than to distribute, right?
Yeah, use the rules.
Yeah. But for this, is it easier to do the cross product first sometimes, or no?
Would you rather do one cross product or two cross products? Boy, that's a good question. And I guess it depends on the application. What I will say is it's important to know facts like this for sure when you're doing different pieces of mathematics. Wow, there's an hour of video. Hope you guys